We will do a small version of a problem I assigned. So I'll call it a speeder and the cop problem. I've given you a much more practical version of this problem in the homework. So this one's a stripped down version of the same problem. So the idea is that somebody is speeding and the cop is going to catch the speeder. The person who is speeding, in this case, is accelerating. And the cop is traveling at fixed velocity, of course, all along a straight line. So the first point that I want you to realize in all these problems is, let's say, when I say somebody catches somebody or somebody meets somebody, so in this case, cop catches speeder, essentially implies that they meet at a unique point, a unique position, at a unique time. So both of them must obviously be in the same spot at some point in time and in some position in space. That's the first thing. So if you miss that part, or if you don't aggressively implement that part, then you will unnecessarily be spinning your wheels without getting to the point. So in this case, let us say that A is speeding. Let us say A starts from rest. And at some x0, some initial point x0, which is, let's say, at 20 meters from some origin. There's a point here, okay? Let's also say that the acceleration of A, this is acceleration of A, is, let's say, I chose a number, small a is equal to 5.00 meters per second squared. Okay? All right. And let's say the cop, in this case I'll denote the cop by C. C, cop, is traveling at fixed velocity. And the velocity is 30 meters per second. Let's call it V, and V is 30.0 meters per second. So, and this guy obviously starts 20 meters behind the speeder. So let me push this up. Let's just make some space. Okay. So the first thing in this case that I'd like you to do is I'd like you to draw some kind of a graphical description because it helps you compute the problem. So let's say the horizontal axis here is time, and the vertical axis here is x. So the distance traveled, or the displacement rather, to be technically correct. Okay? So let us say that this is x0. This is where A starts. Okay, so A starts from rest, and as I described, A starts x0 ahead of the cop. So wherever the cop starts, that can be the origin. So we'll take the origin here to be the place where the cop starts. So the cop is obviously moving at uniform velocity, and it's moving at 30 meters per second. So let us say we graphically describe how the cop is progressing in time with this dashed line. Now let us say that A, which is starting from rest, is going to now accelerate at 5 meters per second square, which means A actually will kind of go like this, like that. Because if A is accelerating, then we know already that distance traveled by A, let's say, can be written as some initial velocity times time plus 1/2 its acceleration times time squared. So we know that. So in this case, as far as the cop is concerned, there is no acceleration. So cop is moving at fixed velocity, and therefore the cop is following this dashed line. The speeder, on the other hand, started from rest. So V0 was 0, right? Started from rest. And this guy is speeding. So if this guy is speeding, that means its distance as a function of time will be a quadratic function, and a quadratic function like this will give you a parabola. And that's also the reason why the blue line describes a parabola. So what you're looking for is you're looking for basically, actually, you can immediately tell that there are two times at which these guys will meet. There are obviously two times, because that's where the two lines cross. So clearly, we should be able to now do something with this problem. So let's go set it up. It's actually relatively simple if you know what to do. So as far as A is concerned, so I'll call this guy the cop C, and this guy is A, the guy who is accelerating. So as far as A is concerned, so let me say A colon just describes that we are talking about A. We can say that the distance traveled to the final point where he gets caught, xf, minus wherever he started, that x0. X0 is already, I said, is 20 meters. So this is actually the actual displacement that A undergoes, and this must be, since it starts from zero velocity, I can use this equation to write 1/2 AT squared, and I already know A is 5.00 meters per second square times whenever they meet, which is t squared. You should be happy that there is a t square, because you should find 2 times in your answer, because they cross paths twice, which means that you need to be getting 2 answers for t. So having a t square is definitely a good thing. Now, I can make this a little bit more precise. I can replace the x0 there by 20, because I already know that x0 is 20. Okay. I should write meters. I feel uncomfortable if I don't write the units here. So that's the story of A. Story of C, on the other hand, the cop is quite straightforward, because the cop is simply moving at fixed velocity. So the final point where they meet, which I'll call xf. By the way, xf will also have 2 values, but that's not very interesting right now. And this is equal to 30.0 meters per second, which is the velocity with which the cop is moving times the time. So now you see you have 2 unknowns. You don't know what xf is, and you don't know what the time is. You have 2 unknowns, and you have 2 equations. So at this point, this becomes a problem that you can solve. So the equations are set up. So in all these problems, when somebody is meeting somebody, one overtaking the other, and so on and so forth, or one missile being launched to essentially neutralize some other missile, the problems are basically structured the same. You have 2 unknowns. One is the position, and one is the time. Yeah? No, you are. Speak a little louder. What did you say after?
We only use your E equals G times D. Is that only if we have a fixed?
That's only for the cop.
Why not? We only use that if you have a fixed constant.
Right. So if something is moving at fixed velocity, you'll use that, right? But because that's the simplest thing to use. For the accelerating car, on the other hand, we don't have a choice because this guy is accelerating. That answers your question, right?
Yes.
Okay. All right. So let's see if we can do this problem. So I will not carry through with a complete solution. I'll just show you how to do it because I think that's good enough in this case. You can do the rest yourself. So I already have an expression for x final, which I can substitute here. And that way I can eliminate x final and set up one quadratic equation in time. So look at the strategy. Once I do that, I'm all set because then I can solve for time in the same way that we have been solving for time lately in the quadratic equation. Guys, don't talk. Shh. Who's talking? So I would just stick this in there. So I can write 30.0 meters per second times time. So that would give me this minus 20.0 meters. So that's the left hand side of this equation. And then I can write this is equal to half of 5 is 2.5. So 2.50 meters per second square times t squared. So clearly I have a quadratic equation and we know how to solve a quadratic equation. So let's organize things. I will take everything to the right. I always like to keep the quadratic term positive. Now I'll not write the units. This becomes a plus because this goes on the right side. Sorry, first I'll write this one. This becomes a minus. So this becomes a minus 30.0 times time. And this becomes a plus 20.0 is equal to 0. So at this point it's the Aryabhatta equation and you know how to solve it, standard quadratic equation. And if you solve it, which I won't, to save some time, you basically, depending upon what approximations you pull to do it by hand or do it with a calculator, you wind up with two answers, as you should, because there are two times. There's a time here and there's a time there. So what you end up with is that the early time, let's call it, the early time I'll write that first, that's roughly 0.80 seconds. Soon after these guys start out, and as you can see, this guy is probably not moving very fast at the time. And the next time turns out to be approximately 11.2 seconds. So as you can see, this problem, although it may look pretty daunting when you take a look at it, it's actually a straightforward problem. The strategy is there's an x and a t that is common. You set up the equations for the two guys and you combine the equations in such a way that you find either x or t first. So in this case, I eliminated xf and I found t first. I could have done the opposite, it doesn't matter. Either way, I would have gotten a quadratic equation. So now I can easily compute xf because I can find xf by using the simpler of the two equations, 30.0 meters per second times whichever time I want, this time here or this time there. Those are the two positions in which they will meet. Any questions? Yeah.
So there's two times because they meet twice?
Yeah.
Why do they meet twice? Just matches in one.
He could have caught him twice. The first time wouldn't make much sense because this guy was probably moving too slowly because it's very early. Right? You don't want the cop to catch you even if you're not doing anything bad. So a cop would probably catch only once when he's speeding at 11 some seconds. Okay? All right. So let me do the second problem that I wanted to do. The second problem, it's almost identical to a problem I gave you guys in homework. The reason why I thought I'll show you how to do it is because it's always a good idea to see some worked out problems, and I think it probably clarifies and boosts confidence and stuff like that. So the problem here is that suppose you have some kind of a well, and let's say you are suspicious that at the bottom of the well there is water. That's the problem I gave. So what you do is you stand here and you drop something. So this thing drops and ultimately hits the water, and as it hits the water there is a noise, and then this noise comes back out and you can hear it at the top. So the question really is, if you know how long it takes between you dropping the rock or whatever and hearing the noise, then whether you can figure out how deep the water is in the well. Okay, so that's the question. So we don't really know why. Let's call this y. This problem is a little bit on the mature side of problems, because if you followed the sign conventions that we have introduced, as far as this problem is concerned, you use it once and you don't use it another time, and I'll tell you why. It's a bit nuanced. So I said you drop the ball, so that naturally that means V0 is equal to 0. So I already gave you some information. You also know that on Earth you have a downward gravity, and the magnitude is 9.80 meters per second squared, and I just put a minus sign here to mod g, just so that we understand that this is 9.80 with a minus sign. All right. So let's say the other information that is given is that the time taken between you dropping the ball and you hearing the sound, in this case, is 7 seconds. 7 seconds then is the total time. Part of that is the time taken for the ball to fall, and part of that is the time taken for the sound to come back up. So let us say we call T1 the time taken for the ball to fall, and then we call T2 the time taken for the sound to start from the bottom and reach your ear. So there are 2 times. So this is a condition that you have arrived at by simply using your watch or phone or something and figure out how long it took. Now, as far as the fall goes, it is pretty simple, because if I start measuring from here, I can call this for now to be my y equal to 0 level, which means, and since I'm dropping it, V0 is 0. So if I'm looking at the kinematic equations, let's recall, whenever you do these problems, you should always have the kinematic equations up here. So first is that distance is some kind of velocity times time. This can be an average velocity. We know that V final is some kind of a V initial or V0 plus acceleration times time. We know that V final square is V0 square plus twice a times some distance, x or y, doesn't matter, depending upon which axis. And we also know that the distance traveled, x, let's say, or y, let's have y here, y is going to be V0t plus 1/2 at squared. So these are my equations. So as far as the drop of the ball is concerned, V0 is 0. We don't know the height, so this equation is ruled out. We don't know V final, so this equation is not going to be very helpful. It's y we are after. So this is the one that we should be playing with. So what we can then say is minus y is minus 1/2 g, and then the first time, the time to fall, is t1, so gt1 squared. So that equation I already know, which means I can also write from here that T1 must be 2y over the value of g without the sign. I'm just putting in the mod. Whether you put in the mod or not is immaterial as far as I'm concerned, as long as you know the correct sign of g as it ends up here. This is just positive. So there should be a root, because I took this 2 here and I divide by g, and this is t1 squared, so this is just 2. All right, so I have an expression for t1 in terms of the unknown y. I don't know what y is. The other thing is that I also know that the sound is traveling from the bottom to the top. Now, here I have to be a little bit careful, because as far as the sound is concerned, the sound is not starting here and going down. Sound is starting at the bottom and coming up. And the speed of the sound, in this case, is the pressure wave propagating upward. So the best way to do this is not really worry about signs, but we can just simply write that the modulus of y, just to make sure it's just the positive value of y, just how big this y is, must then be equal to the speed of sound times the time taken for the sound to come up, which is t2. And the speed of sound actually turns out to be, in air, it's pretty well known. It depends upon the humidity and the temperature, but it's approximately 330 meters per second, or about 1200 feet per second. That's the speed of sound in normal air. Yeah?
Or we can never have to memorize that?
No, I'll give that to you. We should know roughly what the number is, but yes. This is just because it's going down. Remember, our sign convention is that wherever we start the motion from, we set that to be the origin of y. So here it's going down, and we have already defined the downward direction to be negative. G is downward, y is downward. If I were going upward, it will be positive. So in this case, I'm not really playing around with the origin anymore. I just need to describe the distance traveled. It's like a d equal to vt kind of a thing. That's the formula we are using. I'm just interested in the magnitude of the distance traveled, speed times, this is t2. Because that's not total time. That's just the time taken for the sound to come up. So now you see, we have a situation where I know one equation on t2. I know one equation that has to do with t1. And I also know one equation that has to do with t1 and t2 that I haven't yet implemented. So this is one of those problems where we actually have 3 equations to solve instead of 2. And this is very similar to the problem I gave you in the homework. I changed the numbers a little bit. So anyway, so at this point, let's see what we can do. Let us get rid of one of the t's. So from here, I can write, what do I want to eliminate? Let's say I eliminate t2. So let's say I can write y equal to 330 meters per second times t2, right? That's this equation here. And I can also write this as 330 meters per second. T2 is turning out to be 7 minus T1, right? Because now I'm incorporating that relation that I haven't used yet into my equation, and that gives me the advantage of having y written in terms of T1 in 2 different ways. So here y is written in terms of T1, and here also I have y written in terms of T1. So I should be able to do a few things. In fact, I can write this y as half gt squared. so I can write half g t1 square for this y, and this I'm doing from here or here, it doesn't matter. And this is equal to 330 meters per second. Times 7 minus t1. So it is easy to see that you have another quadratic equation. You have a t1 square term, you have a t1 term that multiplies to 330 t1 with a minus sign, and then you have a 330 times 7, which is just a number. So if you actually write the equation out of it, you wind up with the following. I'll skip a few steps because you'll be doing a problem very similar to this in the homework. So something should be left to imagination. So we have 330 T1 minus 2310, which is 330 times 7, and that's equal to 0. Okay? You guys are with me or no? Okay. So clearly you should get two answers for t, and the answer that is completely positive, there's only one answer that's fully positive, and that answer, without calculator I did it, is 6.39 seconds. So in other words, it takes 6.39 seconds for the ball to leave your hand and actually hit the water level. You already know what T2 is, so therefore T2 is simply going to be 7 minus 6.39, which would be approximately 0.61 seconds. And from here you can find y, whichever way you want. So y can simply be computed with the simplest relation. So y can be 330 meters per second times, I'm not being very picky about significant figures here, 0.61 seconds. And if you calculate that, it's about 200 meters of that order. Roughly. Okay? So this is one of the more difficult problems that I would typically assign from time to time. Yes?
How would you know which one is T1?
How would I know what? I don't understand your question. Why that answer?
Yeah, why did you use 0.61?
Oh, no, 6.39 is the time, was the time for T1, right? I specifically defined T1. The equation for T1 and equation for T2 won't be the same. Because you see, T1 involves this relation. So, if I wrote in terms of T2, I would have to replace this T1 with a T2. That would bring in a completely different equation. Again, I would, if I do that, I haven't done that. If I do that, I would still get 0.61. And then I would take 7 minus 0.61 to get 6.3. So there are multiple ways of doing this problem, obviously. There is nothing special about finding T1 first or finding T2 first. As long as you do the algebra correctly, you will get the right result. So there is nothing surprising about that. But just be confident about, how you do these problems. They are not difficult, and most of you have done pretty well from what I can tell. But if you are having difficulties, don't be shy about it, because we are here to help you, and if you don't seek help, there is no way for us to read your mind. All right, so now any other questions before I move on? Okay. Now I'm going to spend a little bit of time in dealing with vectors, because we'll be using vectors pretty heavily. From this point on. So the idea about vectors is that we don't really want to spend too much time, at least too much class time, doing them graphically. Most of the class time and most of the actual applications that we'll be dealing with deal with having to work through vectors algebraically. So normally the way it would work is that I would draw my x and y axes, let's say, and then I would draw some vector, let's say a vector here I can call vector p, and I'm really interested in the direction of p, which is given, and the magnitude of p here, and the direction, which is direction typically with respect to some standardized axis. Directions are normally calculated with respect to the positive x-axis. That doesn't mean that all directions at all times you should calculate with the positive x-axis. That means that when you report the direction in terms of an angle theta, you should write it by default with respect to the positive x-axis. Why did I tell you that? The reason why I told you that is because sometimes it may not be the most convenient thing to actually calculate something with positive x-axis. It may be much easier to calculate it with respect to some negative x-axis or negative y-axis or whatever. So there is no reason for you to invent your difficulty when you don't have to. You go ahead and calculate your theta, your angle, whichever way you can get it easily and with making least amount of mistakes. But when you report it with respect to the positive x-axis. That's very important. In fact, the problem I have given you in this homework set forces you, well, it doesn't really force you, encourages you to do it that way, which I just said. Do it in the most convenient way, but then report it in the way that you should report it with respect to positive x-axis. For example, if the vector were pointing that way, you see the angle with respect to positive x-axis will be a large angle, right? But wouldn't it be more convenient if you could quickly calculate this angle? Maybe it's much easier to calculate. Well, if I were you, I would calculate this angle, make my life easy, and then I would say, well, this is 90, this makes it 180, this makes it 270. So from 270, I just subtract this angle, and that automatically gives me this large angle. All right? So that's what I'm saying. Anyway, we'll deal with it in a few minutes. So at any rate, what I'm going to do, as I told you last time, is I'm going to drop a perpendicular here, and then this will be the x component of p along the x-axis, and this will be the y component of p. Of course, if this is the y component of p, I can always complete the parallelogram and realize that that means this also is the y component of p. If this is the x component of p, that means this also is the x component of p. Right? So let us say this angle I call theta. Sine of theta is defined to be perpendicular. Perpendicular is the angle opposite, is the side opposite to the angle. So that's what a perpendicular typically means. So in other words, if I draw some kind of a triangle here, and if I select this as my angle of interest, let's call this angle phi, then the perpendicular will be opposite to phi, which means this will be the perpendicular. Adjacent will be this one, and that's pretty obvious because this one obviously is the hypotenuse of a right triangle. You have no choice there. So you know the perpendicular and you know the adjacent. But keep in mind that perpendicular depends upon which angle you have chosen. If you choose this angle, that's your perpendicular. If you choose that angle, that's your perpendicular. So in this case, sine of theta is defined to be perpendicular over hypotenuse, so that will be your py over p. Likewise, cosine of theta is adjacent over hypotenuse, so px over p. And a very useful angle is tan of theta, which is sine of theta divided by cosine of theta, and that therefore is py over px. So whenever you calculate an angle theta, it doesn't have to be that way, but almost in all occasions you end up calculating tan of theta, and then you say theta is arctan or inverse tan of this ratio py over px. Mind you, py over px is a pure number. It's a ratio of two lengths or whatever the units are. So theta doesn't have, sine of theta is a ratio, cosine of theta is a ratio. Now you also, because it is a right triangle, you also know from Pythagoras' theorem that p squared is px squared plus py squared, which then means that p itself is px squared plus py squared, square rooted. And whenever you take a square root, keep in mind that you may have to worry about a minus sign. So let us do a problem, simple problem, but not so simple that it has no value in terms of messages taken home. So let us say that I draw my x and y axis, so that's my positive x, that's my positive y, my negative x, and that's my negative y. And let's say I have two vectors. I have a vector here, v1, and let us say, for argument's sake, although it doesn't quite look like it, but let's say this angle is 30 degrees, and exactly 180 degrees on the other side, which would mean at 210 degrees, I want to put some other vector here. Now you might ask me, why do you want to do such a simple thing? And that's because I really want to show you the nuances of the algebra involved. So therefore this angle is 210 degrees. So as you can immediately see, the way I have set up this problem, the vectors are equal and opposite. Vectors are unequal and opposite. So in this case, v1 seems a little bit larger than v2. So without doing anything, just by looking at it, you can pretty much tell that what will happen if you were to add these two vectors is this guy will win over that guy. So at the end of the day, you'll end up with a teeny vector here, which is the difference in magnitude between these two guys, and that will be at the same angle as v1 is at 30 degrees. So you know the answer. By looking at this problem pictorially, you know the answer. Now, so this underscores the importance of drawing pictures. So in physics, and you will see this more and more as you go along, it is very important that you have an image, you have a movie, if you will, if necessary, of what's really happening in a situation. And the way you solve the problem should emulate that movie or that picture. Because if you don't have the picture, there is an almost 99% chance you will make an error very easily. So you'll find that physicists draw pictures a lot. And in some problems in homework 2, I have actually drawn pictures and attached them. In some of them I have not, because I want you to draw the picture. Okay, so and you will figure out very quickly what is the right picture and how to draw it, because if you can't do that, then you'll have, obviously you won't get the right result. Yeah. It's 180 plus 30. It's exactly opposite to the. So if this is 30 and if it's exactly opposite, you add 180 more, so it's 210. So I'm now going to quickly go through this problem. So basically I'm going to draw perpendiculars here and there and so on. And so I can write, without really doing too much picture drawing, that v1x, which is this piece of v1, is going to be V1 cos 30, because the angle is 30, and V1y is going to be V1 sine 30. So cos 30 turns out to be root 3 over 2, and I'll show you how to calculate these, and this you have to know. And sine 30 is a half. Okay? Sine 30 is a half, and that's root 3 over 2. Likewise, I can do the same thing for V2x. V2x would be V2 cos 210. I will just do it the old-fashioned way, make it cos 210. I could have taken this angle and constructed it and put a minus sign, but that's okay. And V2y will be V2 sine 210. Now, before I proceed any further, I need to teach you a few things. So, all you really need to know in trig is that you have a right triangle, right? And you essentially have, let's say, a side A and a side B and a side C, and this is the 90 degrees, and that A square plus B square is equal to C square. So that's, of course, the start of everything. That's your Pythagoras theorem. Now, let us say that this angle is theta. Then, of course, we know that from what I've already told you, that sine of theta is going to be B over C, cosine of theta is going to be A over C, and tan of theta, which is sine over cosine, is simply going to be perpendicular over adjacent, which is B over A. So this is very simple, right? Nothing very mysterious involved here. Now, what you need to know besides that are the standard angles that we work with. So for example, let us say you need to know the sines and cosines of certain theta values, the simple ones. I don't expect you to not use a calculator if you're calculating sine of 15 degrees. But I expect you to not use a calculator when you calculate sine 30 or 45 or 60 and so on. So the simpler ones are 0. Sine of 0 is actually 0. Cos of 0 is actually 1. Okay? You can just look at the triangle and figure it out. The next one that is very simple is sine of 30. And sine of 30 is actually a half. And then cos of, I'm doing it in a strange way. I think I'm going to confuse the heck out of you. Let me, sine of 30. Let me just do the sine first. Sine of 30 is a half. Sine of 45 is 1 upon root 2. 1 upon root 2 can also be written, if I multiply upstairs and downstairs with root 2, as root 2 over 2. Sine of 60 is root 3 over 2, and sine of 90 is 1. So if you look at it, you can remember it in the following way. So it's basically root 1 over 2, root 2 over 2, root 3 over 2. So sine 30, sine 45, and sine 60 just follow a beautiful pattern. So as sine goes up, as the angle value of sine goes up, this number goes up. Cosine is just the opposite. So in other words, if I have a cosine, what I'll have for cosine, and the actual value, cosine of 0 will turn out to be 1. Cosine of 30 is going to turn out to be root 3 over 2. Cosine of 45 has the same value as sine of 45. that's root 2 over 2, and cosine of 60 will turn out to be half, which I can call root 1 over 2. And then cosine of 90 will turn out to be 1. So you see the patterns are just opposite. And since tan is sine over cosine, by knowing sine and cosine, you can work out the whole thing. So, yes. What? Cos 90, yeah. Cos 0 is 1. Thank you. No, this is fine. Cosine of 90, cosine of 90 is 0. I'm sorry. Yeah, thank you. Any other questions? Don't panic. You'll get it. If you're not good at trig, yes.
Cosine of 60, 1 over 2, not the square root of 1 over 2?
Isn't that the same thing?
Yes.
That's why I wrote it like that, so it's easier to remember.
That's why you're the professor. That's why you're the professor.
Yeah, it's just easy to remember if you have the root pattern following. If you can write it as, I normally write it as half, but when I introduce to students, it's easier to remember if I write. Any other questions? Great. Yes? Yes, we have a quiz every day. It's in the syllabus. Every day we have a quiz. Okay, so, but there is something that you should know, because otherwise you'll have trouble computing these if I throw it to you. Guys, don't think I am not watching you. I'm very good, even though my vision is not very good, but I can figure out who is doing what. So, if I have a situation like cos A plus B, let me first do sine A plus B, that's the easier one. You will need to use that quite a bit. If I have sine A plus B, then how to combine that is the following. The formula is sine A cos B plus cos A sine B. And if I have sine A minus B, then all you need to do is make it a minus sign. Why did I tell you this? Because I'm going to need that to calculate sine 210. Because sine 210, if I don't have a calculator, is 180 plus 30. I know what sine 180 is, and I also know what sine 30 is. So similarly, you also need to remember cos A plus B. This one is different. This one is cos A cos B. But when this is plus, you stick a minus sign here. And see, the pattern is different, sine A sine B. And when you have a minus here, this becomes a plus like this. So when I write it in the following form, that means the signs actually flip. So cos A plus B is cos A cos B minus sine A sine B. But cos A minus B is cos A cos B plus sine A sine B. That's what this flipped sign means. This means they are synchronized. Okay? So actually, I can now calculate cos 210 and sine 210. It turns out that cos 210 is minus root 3 over 2. And sine 210 is minus 1/2. The reason why the minus sign comes in is because cos 180 turns out to be minus 1. So you need to also keep in mind that in trig, all is positive between 0 and 90 degrees. And sine is the only quantity that is positive from 90 to 180. Tan is the only quantity that's positive in the third quadrant. And cos is the only quantity that is positive in the fourth quadrant. So these are more practitioners' rules, but we'll go over them later on. So essentially what happens is sine of 0 is 0, sine 90 is 1. It can't be more than 1 because of the right triangle there. So now it starts decreasing. So sine goes from 0 to 1, and 1 to minus 1, minus 1 to 0, and 0 to 1. That's the pattern. Anyway, you can look it up. I'm not going to go too far into this. But the bottom line is that I can now, let me go to the other board. Bottom line is that to calculate the resultant of V1 and V2, I need to find the vector V, and I need to first find the x component of the vector V. So you see, x component of vector V will be V1x to the right, and in this case V2x, which will wind up on the other side. So it will turn out that if I put in the values, it will be V1 root 3 over 2 times V2 minus root 3 over 2. Likewise, Vy will be V1y plus V2y, and that will be V1 times a half plus V2 times a minus half. So therefore, I should be able to write this thing as V1 minus V2 times root 3 over 2, and I should be able to write this as V1 minus V2 times a half. And it will turn out from what we have already shown that the actual vector V, that's the resultant of the two vectors, V1 and V2, is V1 square, Vx square plus Vy square, which we have just calculated. And so that would mean that Vx square is V1 minus V2 times 3/4, because root 3 over 2 squared is 3/4. And the other one would be V1 minus V2 squared times 1/4, which means that V would basically be V1 minus V2 in this case. V1 minus V2 squared followed by a half power square root. So that's basically the difference. Remember, we already found out that we wind up with just the difference of the two vectors because the vectors are pointing equal and opposite. So we have just confirmed the expected result, and the tan of theta in this case is Vy over Vx. So let's look at Vy, that's my Vy, that's my Vx. And if you work out this calculation, you'll get an answer of 1 upon root 3. So 1 upon root 3 for tan is going to be for 30 degrees. Because you see, sine 30 is half, and cos 30 is root 3 over 2. So tan 30 is going to be 1 upon root 3. So tan 30 equal to 1 upon root 3 means that the angle in which the resultant would end up in is going to be along V1, which is precisely what we expected because V1 is the bigger vector. So what you have is the difference between the two vectors. Let's say it is a stubby little vector like this, at the precise same angle as 30, which is what we were expecting to find. So almost all the vector problems that you'll be doing, and you'll be doing a good bunch of them as we move along now, will have to be done in the same way. So you first break down the vector into x and y pieces, and then you individually add the x's, individually add the y's. I want you to get some practice in this. I'll try to assign you some problems as we go along, because if you're not practiced up, there is a near 75% chance that you will make completely avoidable errors. And this is something that I don't want you to unnecessarily suffer from. So you'll get a fair amount of practice problems. All right, let's go to the quiz.